Okay, back to the photoelectric effect. So normally I have my metal plate over here. So should be, for example, this is the zinc plate that I've used in my mini experiment, DIY experiment. But the effect is very subtle, so you won't be able to see a detrimental effect of that. So that's why it is not possible for me to to demonstrate in front of you, because we need a lower temperature. Maybe in the UK or in the US it is possible. So here, for instance, I have my photon coming in. So the zinc will absorb, not really absorb, but I will say absorb for the first place. So when I zoom in, okay, this is my zoom in version. Okay, it is shaky. So I have my nucleus. I have many nuclei here, and the electrons are revolving around the nucleus. So I have my electron here. So once the photon is being absorbed by the electrons, the electron will attain the energy of E equals to hf. This is something that you have learned during your high school, I suppose. So h is the Planck's constant, and f is the frequency of the light. Sorry, frequency of the light, of course. So meaning to say, once it has attained the energy, it will get excited, it will oscillate, and then it will leave the atom, provided that the energy of the electron is greater than the work function. Meaning to say, I have my hf as the total energy should be equals to the kinetic energy of the electrons plus the work function. Okay? Because when you give an amount of energy which is about hf to the electron, then that energy will be used to oppose the nuclear force. So we have the nucleus here. So the electron is bounded in the nucleus because of the nuclear force. So you need to spend some energy from the hf, from here, you need to spend some energy in the work function. So different materials has the different work function. For example, if I have zinc, I have a value. And then if I say gadolinium, which has a lower work function, it is easy for the gadolinium to release the electrons because of the work function of gadolinium is lower than the work function of the zinc plate. For example, if I replace this with gadolinium, then the work function is lower. GD is lower than the work function of zinc. So the unit is joule, yeah? My W has the unit of joule or electron volts. The kinetic energy is in joules, or if you are a nuclear physicist, it is better if we use the electron volts, because the energy is equal to charge times multiplied by the volts. So the energy is, the unit of energy is electron volts. So you have to shift your brain at the moment. So once I have given my hf to the electrons, then the electron will use some of it to oppose the nuclear force. So that amount of energy consumed is inside W, okay? And then the remaining energy from hf is given by K, which will be used by the electron as a kinetic energy. So that's the idea. So if I were to draw the Feynman diagram for the photoelectric effect, I would do this. So I have my photon here, and then I have my node here, and then this is my electron, which is inside the atom, and then this is my photon. The photon oscillates the electrons, and then the electron attains the energy. So now it becomes, I'm shaking. Okay, now it becomes a new electron, but with a higher energy. So the energy now is given by K. Initially, the kinetic energy is 0. Okay, so the energy here for the photon is equal to hf. So this is the time axis. As the time progresses, this will happen. Okay, so normally in the diagram we use the wavy line for boson. Okay, for photon. Photon is under boson, so we are using the wavy line. But for electrons, which falls under the fermion, you will learn this later in the next courses. So we will use a straight line. If we have an antiparticle, which is the positron, for example, it is an electron, not an electron. I mean, it has the same mass as electron, but the charge is positive, so it is positron. So you have to use the reverse arrow. So that's the idea. So if you could remember this, I mean the diagram here, then it will be easy for you to remember the process. Okay. For a quantum physicist, this is also important for them to simplify the equation, because they need to evaluate the integrals. So from the mathematical equation, it is not easy for them to visualize things, so they use the Feynman diagram. So for a Feynman diagram, this is the node. So each node must have 3 lines. For example, it's coming from here, and coming from here, and then going outside. So here I have to put star, because we need to say this electron is being excited. Okay, that's the idea. So that's it. I hope you are okay with the photoelectric effect. Okay? Okay, so normally we have the wave expression. So now, because I'm talking about the electromagnetic wave, so I'm going to use my electric fields. I need you to remember back your basic physics, which is the electric field. So I have my electron here. Once my electron is moving from point A to point B, basically it is producing the current. So the movement of the electron from here is to here, and the current is going towards that direction, I mean the opposite direction. But at the same time, this electron is inducing the electric field. That's why we are having the communication tower. For example, you are the radio DJ. You are sitting next to the signal generator. The signal generator itself is actually consisting of the AC current, the alternating current. So when the electron moves back and forth like that, it is actually generating the electric field, right? We are using, for optics, we are using the EM wave to represent the light. Okay, so the electric field, is given by E naught cosine of omega t. Sorry, I'll use this backwards. Sine of kx plus minus omega t. Okay, omega t. We can also use E naught sine of kx plus minus omega t. Well, you can also use omega t first in front and kx behind. Well, it is just a manipulation of equation, but basically they are the same. Okay? But I prefer using cosine, because cosine is friendly. For example, if I have cosine of negative theta, which is equals to cosine of theta. So basically it is friendly to me. It makes my mathematics easy. That's why I prefer cosine. Well, in the actual case, I prefer the exponential form, because it is much more easier. I'll explain about exponential form later. But now I want to make you understand whether the wave is propagating towards the positive x direction or the negative x direction. So I have my oscillator over here. It is oscillating along the z direction, but eventually the wave seems to be moving in a certain direction. Okay, the wave seems to be moving in a certain direction. For example, the sea wave, right? So if you have a stationary object on the surface of the water, and then the wave comes, and then of course the object will oscillate in the vertical direction. But the wave itself seems to be moving from one place to another. Okay, so we will be able to know the direction of the wave by using the positive and negative sign over here. So I need you to refresh your mathematics. Okay, for example, if I have a function f of x, okay, function f of x, so I have my curve over here like that. So if I say, let's say if I put an offset to the argument, if I put an offset to the argument x, for example, x minus a, so meaning to say the axis is moving towards the negative direction. So my axis here is moving towards the negative direction. So it seems like my function is moving towards the right hand side. Right? I hope you get this idea. If I have my axis over here, and then if I take an offset, for example, the negative a here, meaning to say I have moved my axis towards the negative direction. So if you have the negative sign, you are taking, meaning to say you are taking the axis towards the negative direction. If it is positive, then you are actually taking your axis towards the positive x direction. Remember that, okay? Now I'm going to manipulate the equation for you. So as you know, the velocity of the wave is equals to f lambda, which is also equals to 2 pi f multiplied with lambda over 2 pi. So the 2 here, 2 pi and 2 pi at the bottom will cancel off. And then eventually I have my wave number, my temporal wave number, and then this is my spatial wave number, k. W and k, spatial. This is temporal. Okay? So normally for an electromagnetic wave, the speed is the speed of light, right? C, 299,792,548 meters per second. So basically, C is equals to Wk for EM wave in vacuum. So here, I have E equals to, let's say if I use the cosine, okay? E equals to cosine, sorry, I forgot to put. E equals to E naught cosine of kx plus minus, so I'm replacing omega, so meaning to say now my omega is equals to, sorry, this is inverted, so should be omega over k, because k is equals to 2 pi over lambda, right? So it should be over k. So my omega is equals to kc. Okay, my apologies for the mistakes. So omega equals to kc. And then I substitute my kc inside my omega here. So now it becomes kc times t. And then I bring my k, my wave number, spatial wave number outside. Then I'll have E cosine of k x plus minus ct. So if you want to know whether the wave is moving towards the positive direction or negative direction, the movement of the wave actually depends on time. So as basically times will be greater than 0. The time will progress from 0 to infinity. For example, let's say if I have E naught cosine of kx plus ct. So if I have my t increasing, because the value of t is increasing from 0 to infinity, because that's the normal thing. It shouldn't be going backwards in time. So the time is moving forward. So the value here keeps on increasing. But if I use the positive sign, meaning to say I am bringing my, let's say this is my wave, okay? This is my axis, this is my time axis. I am actually bringing my axis towards the positive x direction. So meaning to say, it seems like our wave is moving in the opposite direction. But the time is increasing, then the value here keeps on increasing and increasing. So you will see your wave is, you will see the axis moving towards the positive x direction all the time. So the wave is moving towards the negative direction. This is something that you don't have to remember. You just need to manipulate the equations and you'll understand whether it's moving forward or backwards. Any specific question on this? Okay. And then now I'm going to teach you about the exponential notation. So normally, for the complex number, z is a complex number, we have in the form of a plus bi, where I is the square root of -1. This is just a mathematical convention. Yeah, you don't have to think further. Why is negative sign square root of? It's just a mathematical convention. Because sometimes when we want to solve an equation, we are arriving at the square root of -1. So if we don't invent the imaginary number, then we won't be able to solve the equation. So meaning to say, for a physical world, for a physics problem, we will encounter imaginary number, even though it is not logical. But to solve the equation in physics, you will came across the imaginary number, and then at the end of the day, you will have a solution which is a real value. But we need the imaginary number in between to enable us to solve the problem. I hope you get the idea, yeah? Of course, I can replace this with cosine of theta plus sine of theta, and then I put my imaginary number in front, like that. Okay? So this is basically equivalent to the exponential of I theta. I'm not going to derive why it is so, because you need to go through the mathematics, and I'm going to waste my time here. But for now, you just accept it as it is, and then if you have the question, why are we using the exponential of I theta, you can ask your calculus, or I think for complex analysis under another lecture. So this is something related to the Taylor series, yeah? Taylor series. Then you will end up with the guy over here. Okay? Just bear in mind. So, meaning to say, I have two sinusoidal components, my cosine and sine over here. So I can also write my wave equation in the form of E0. So E0 is the amplitude, yeah? E0 is the amplitude of the wave. And then I have E, I, kx plus minus omega t. You don't ask me, why are you using the exponential? I don't think it's logical because it has the imaginary number. This is just a language, yeah? This is just a language, the mathematics to represent the wave. Just the language. So I know there is the imaginary number, but we want to represent the oscillation. That's it. So in mathematics, we have a few functions that are oscillating, the cosine, the sine, as well as the exponential, because of this. Okay? The next objective is for you to take note that when light travels in a medium, in a dense medium, then the speed of the light will be reduced. You have to accept that law first. I'll explain later why. But remember, yeah, those behind, remember, the speed of light in a medium is lower than the speed of light in the vacuum. Let's say if I have a glass, for example, a prism, the speed of light inside the prism is lower than the speed of light in the air or in the vacuum. The speed of light in the vacuum is greater than the speed of light in the air. Okay? Remember this. And then next, you have to be able to differentiate between the group velocity and the phase velocity. But remember, the phase velocity is the velocity of your peak. Your wave has many peaks, right? The velocity of the peak, remember the velocity of the peak, yeah, is actually the phase velocity. For the group velocity, which I'm not going to explain further here, is something different. I have my wave, a chunk of wave or wave packet, which is moving at a certain speed. But there is a sine wave inside, or the cosine or the exponential wave inside, but the peaks are moving at the different speed compared to the group, right? I'll show you an example here. Let me show you. I have downloaded it is easy for you to see here. For example here, remember, you have to remember, yeah, the definition of phase velocity. The phase velocity is the speed of your peaks. So here my phase velocity is equals to my group velocity. The entire thing is the group. I mean the entire packet. The entire train is moving at the group velocity, but the velocity of the group is basically equals to the velocity of the phase for this particular example. So you can see the blue dot is moving together with the group. But now I have my phase on the right hand side, I have my phase velocity, which is moving in the opposite direction with the group velocity. So you can see that the peak is moving towards the left hand side, but the group is moving towards, it is quite confusing. The group is moving towards the left hand side, but the peaks are moving towards the right hand side. Do you get the idea? So this is an example where we have a stationary packet, so the group velocity is equals to 0. The blob, you know the blob, B-L-O-B, blob. The blob is staying there, it is stationary, but the peaks are moving. So the phase velocity is clearly not equal to 0, but the group velocity is equal to 0 for this particular scenario. So your phase velocity is basically equals Vp is equals to F lambda. F lambda is your phase velocity, not the group velocity. If you want to derive the group velocity, then you need to have a more complicated equation. For example, here the speed is given by omega over k, right? This is omega over k. I've explained in the previous slide over here. Okay. So meaning to say, this is the phase velocity, but for the group velocity is given by d omega over dk, which is more complicated. Okay. When light enters in the medium, so I have my medium over here, pink in color. And the thickness of my medium is, well, let's say it's delta x. And then I have my light beam coming from here to here at the velocity of c. So assuming that this is vacuum. This is maybe the glass. And then when it enters the medium, the glass, it will travel at the speed v. And then when it leaves the medium, it will travel back to c. When the light enters the medium, it will interact with the electrons revolving around the atoms. I'll show you in the drawing here. So I have my nucleus in the middle. So my electrons are revolving around. I'm using the basic model, yeah? Basically, an atom doesn't look like this. It is a field. I do not know. So basically, let's assume that the electrons are the electron is moving around the nucleus. So I have my electromagnetic wave. over here, interacting with my electrons. So you remember, like your handphone, you have the electrons inside your handphone. So you have a signal, electromagnetic wave coming through the antenna of your handphone, and then that electromagnetic wave will oscillate the electron, right? So the electron, once it receives the light, it will also oscillate with the light. Because light is an electromagnetic wave, so the electrons will oscillate up and down because of that. Are you agree with me? Okay, but the electron itself is an electromagnetic wave generator. Once it moves back and forth, it is basically creating a current. So a new EM wave is being generated. You got the idea? So it is basically receiving the initial photon, the light, and then when it moves, it is basically generating another photon. And then I have my photon over here, keeps on moving within the medium. It keeps on moving. It is not affected by the electrons, right? It is there. The EM wave here is still there to oscillate the electrons. But the electron is not absorbing the EM wave. No, it is not like the photoelectric effect, okay? It is just moving, and then, of course, the photon leaves the electron just like that. That's why light can penetrate through mediums. So here I have an extra EM wave created due to the oscillation of the electrons. The two EM waves here will superimpose, such that the combination of the two waves looks like a new light that travels at a slower speed. I can show you an example why does light, when the light superimpose. Superimpose means you add the two waves together. I can show you the example here. Let's say 5. And then I'm fixing the frequency because the frequency of the new photon is basically the same as the frequency of the incident light. This is because of the force-driven oscillation, where you have learned this under Dr. Dian. Later I'll show you. So for example, if I change the wavelength to 3, if both have the same wavelength, then the speed of the resultant wave will be the same. This is, the bottom one is simply this one plus this one. It is basically E cosine of kx minus omega t plus E cosine of kx minus omega t. So you will have 2 omega naught cosine of kx omega t. E1 plus E2. So the amplitude will double because of 2 E naught. So that's why when you see here, the amplitude doubles. So I have set to 5. Initially, I've set to 5 for the incident light as well as the emitted photon. But this basically, the amplitude should not be the same. This is just an example, just to show you that light slows down when they superimpose. Okay, now let's say if I change the wavelength of the emitted photon, maybe I change it to 1. So here I have a funny waveform, which is my light. The light that you see when it travels in the medium. This light, the waveform here, the last one is basically just an example. Yeah? It's basically the light that you see in the glass. So this one is the incident light. This is the emitted light because of the oscillation. And then what we see is the resultant, the superimposed. Because our eyes cannot see the two waves here. What we see is the superposition of the two waves. Can you see here? This is moving faster. When this guy superimposed with this guy, then we have a new guy which is moving at a slower speed. So when light enters the medium, it will oscillate the electrons, then the electrons will generate another light wave, and then in our eyes we are looking at the superposition of both waves, this one plus this one. So the resultant wave is this, which is traveling at a slower speed. So that is the reason why light travels slower in the medium.